Natural language processing with large language models. The Transformer Revolution. Hi everyone, and welcome back to our journey into the world of natural language processing, or NLP, as it's often called. If you've been following along, you know we're diving deep into how machines can understand and work with human language. Today, we're starting with a pivotal moment in NLP history, the Transformer Revolution. Have you ever wondered how computers went from struggling to understand simple sentences to writing essays, summarizing books, and even holding conversations? Well, that's exactly what we'll unpack in this video. Let's get started. Limitations of previous NLP models. Now, before we talk about transformers, let's take a step back. Think about this for a moment. How would you teach a machine to understand language? Early approaches were, well, let's just say they weren't perfect. For decades, researchers relied on models like recurrent neural networks, or RNNs, and their cousins, LSTMs. These models process text word by word, kind of like reading a book one sentence at a time. But here, the problem. Imagine trying to understand a paragraph if you could only focus on one word at a time. It's slow, right? And it gets worse. These models struggled with long-range dependencies. That means if a word near the beginning of a sentence was important for understanding something at the end, the model might lose track of it. On top of that, training these models was sequential. You couldn't process multiple words at once, which made them hard to scale. Let me emphasize this. Scalability was a huge limitation. As datasets grew larger, these models just couldn't keep up. So what changed? This brings us to our next point. How attention mechanisms change the game. Enter the attention mechanism. Now, attention isn't just some fancy buzzword. It's a game changer. Imagine you're reading a book and you underline key phrases or ideas to help you remember them later. Attention does something similar for machines. Instead of processing every word equally, attention lets the model focus on the most relevant parts of a sentence when making predictions. Here's an analogy. Think of attention as a spotlight in a dark room. The model shines this spotlight on specific words or phrases that matter most for the task at hand. For example, if you're translating a sentence from English to French, the model might pay extra attention to nouns and verbs while ignoring less critical details like articles. This was a breakthrough because it allowed models to handle long-range dependencies much better. Words that were far apart in a sentence could now talk to each other effectively. But the real magic happened when researchers combined attention with a new architecture called the transformer. And scalability of transformers. Now let's talk about why transformers are so powerful. One word. Remember how I mentioned earlier that older models process text word by word? Transformers don't do that. They process entire chunks of text all at once. Think of it like this. Instead of reading a book one sentence at a time, you're skimming through multiple pages simultaneously. This makes training much faster and allows us to work with massive datasets. And because transformers are built around attention mechanisms, they can still capture relationships between distant words, even when processing everything in parallel. Let me pause here and highlight this, is what makes transformers scalable. Without it, we wouldn't have the large language models we see today. This ability to scale has opened up entirely new possibilities for NLP. Breakthroughs enabled by transformer architectures. So what have transformers enabled? A lot, actually. They've laid the groundwork for some of the most impressive advancements in AI. For instance, they've improved machine translation, text summarization, and even question-answering systems. But here's the kicker. Transformers aren't just limited to text. Researchers have adapted them for images, audio, and more. This versatility has made transformers the go-to architecture for many AI applications. Before we move on, let's recap quickly. Transformers solved two major problems with older models. They introduced attention to handle long-range dependencies, and they enabled parallel processing to make training faster and more scalable. These breakthroughs set the stage for everything that came next. Pre-training on massive text corpora. All right, let's shift gears now. We talked about how transformers work, but there's another piece of the puzzle that's just as important: pre-training. Have you ever wondered how models learn to understand language without being explicitly taught grammar or vocabulary? That's where pre-training comes in. Unlocking general language, understanding with self-supervision. Here's the thing: humans learn language by being exposed to lots of examples. We hear people talking, read books, and pick up patterns over time. Machines can do something similar through a technique called self-supervised learning. In self-supervised learning, the model learns by predicting missing pieces of text. For example, imagine taking a sentence and masking out a few words. The model's job is to figure out what those missing words should be. This process is called masked language modeling, and it's one of the key techniques used in pre-training. Another technique is called next sentence prediction. Here, the model tries to predict whether two sentences follow each other logically. Both of these tasks force the model to learn about syntax, the structure of sentences, and semantics, the meaning behind words. Why is this important? Because it gives the model a broad understanding of language before it's fine-tuned for specific tasks. Let me emphasize this: pre-training is like giving the model a solid foundation to build on. Capturing rich semantic and syntactic knowledge. Now here, where things get really interesting. Through pre-training, models don't just learn surface-level patterns, they capture deep semantic and syntactic knowledge. What does that mean? Well, semantics refers to meaning. For example, the model learns that cat and dog are both animals, but they're different kinds of animals. Syntax, on the other hand, is about structure. It helps the model understand how words fit together to form sentences. This combination of semantic and syntactic knowledge allows the model to generalize across tasks. For instance, a model trained on general text can later be fine-tuned for specialized domains like medical or legal documents. Emergent abilities of pre-trained language models. And then there's the concept of emergent abilities. These are capabilities that arise naturally during pre-training, even though they weren't explicitly programmed into the model. For example, some models develop reasoning skills, the ability to generate coherent stories, or even basic arithmetic abilities. Think about this for a moment. These models weren't designed to reason or solve math problems, yet they can do it to some extent. How cool is that? Emergent abilities show us just how powerful pre-training can be. Let's do a quick recap before moving on. Pre-training uses techniques like masked language modeling and next sentence prediction to give models a broad understanding of language. This process captures rich semantic and syntactic knowledge, enabling the model to perform a wide range of tasks, and sometimes even surprise us with emergent abilities. The rise of large language models. All right, let's wrap up this module by talking about the rise of large language models, or LLMs. These are the giants of the AI world, and they're transforming how we approach NLP. Scaling up model size and training data. The first thing to note about LLMs is their sheer size. We're talking billions or even trillions of parameters. Parameters are like the knobs and dials inside the model that help it make predictions. More parameters mean the model can learn more complex patterns. But it's not just about the model size. LLMs are also trained on massive amounts of text data. Imagine feeding the model the entire internet, or at least a significant chunk of it. This combination of large models and vast datasets has led to unprecedented performance gains. Let me pause here and highlight this. Scaling is the secret sauce. Bigger models trained on more data tend to perform better. It's not always linear, but the trend is clear. GPT, BERT, and other influential LLM architectures. Now let's talk about some of the big names in the LLM world. You've probably heard of GPT and BERT. GPT, developed by OpenAI, is great at generating text. It can write essays, answer questions, and even create poetry. BERT, created by Google, excels at understanding context. It's particularly good at tasks like question answering and sentiment analysis. Other influential architectures include T5, Albert, Electra, and BART, each bringing innovations such as improved pre-training objectives, revised model architectures, or more efficient training paradigms. These models have significantly advanced the field of NLP by enhancing performance, scalability, or adaptability across a range of language tasks. These architectures differ in how they use transformers, but they share a common foundation: attention mechanisms, pre-training, and scaling. Together, they've pushed the boundaries of what's possible in NLP. Capabilities of LLMs in comprehension, generation, reasoning. So what can these models actually do? Quite a bit, as it turns out. They can comprehend complex texts, generate fluent responses, and even demonstrate basic reasoning skills. For example, you can ask an LLM to summarize a scientific paper, and it will likely produce a coherent summary. Or you could ask it to brainstorm ideas for a project, and it will come up with creative suggestions. But here's the catch. While LLMs are incredibly powerful, they're not perfect. They can sometimes hallucinate facts or struggle with nuanced reasoning. Still, their capabilities are remarkable given how far we've come in such a short time. Implications for NLP application development. Finally, let's talk about the implications for NLP application development. With LLMs, developers no longer need to build custom models for every task. Instead, they can fine-tune a pre-trained model to suit their needs. This saves time, reduces costs, and opens up new possibilities for innovation. Think about this for a moment. What could you build with access to a model that understands and generates human-like text? The potential applications are endless, from chatbots and virtual assistants to content creation tools and beyond. Wrapping up. All right, let's recap one last time. LLMs are the result of scaling up model size and training data, building on architectures like GPT and BERT. They excel at comprehension, generation, and reasoning, and they're reshaping the landscape of NLP application development. That's it for this module. I hope you found this discussion insightful. In the next module, we'll dive deeper into practical applications of these concepts. Until then, happy learning.